Welcome and thank you for joining. In this lesson, we'll look into graphing rational functions. Our focus will be on graphing rational functions of the form quadratic over quadratic or linear over quadratic. As we have mentioned in the prior lessons, rational functions are characterized by their asymptotes. So to draw the graph of a rational function, we always start off from finding the asymptotes. So far, we have looked into rational functions that have vertical and horizontal asymptotes. And to find the vertical asymptotes, we follow two very simple steps. Step number one, we set the denominator equal to 0 and we solve for x. So that will give us the restrictions on the domain of the function. And based on these restrictions, we state the vertical asymptotes. The vertical asymptotes are always located at x equals restricted values. If a function has one restriction, then it will have one vertical asymptote. Two restrictions, two vertical asymptotes. No restrictions, no vertical asymptotes. So based on the number of restrictions, the graph of a function will produce an asymptote. Horizontal asymptotes are found when the y values become constant or stop changing as x approaches infinity or negative infinity. So to determine the horizontal asymptotes, what we do is we allow x to approach either positive or negative infinity, and we evaluate the values of y. And usually, when a function has a horizontal asymptote, the y values will approach a constant number. And once we figured out the constant number the function is approaching to, then we state the horizontal asymptote as y equals that constant number. Now, in the prior lesson, so the lesson before this, we looked into the graphs of functions in the form y equals linear over linear, so ax plus b over cx plus d. And we made a small little discovery there. We found out that the horizontal asymptote was at y equals a over c, which is the ratio of the leading coefficients, the numerator and denominator. So we will extend this idea to help us determine the horizontal asymptotes in functions where we have quadratics in the numerator and in the denominator. So the process will be very similar to the one that we followed in ax plus b over cx plus d. So step number one, I will follow the instructions and I will let x approach infinity. So when we say infinity, it can be either positive or negative infinity. And I will determine the values of y. So if we have x equal to infinity, then we have infinity squared plus 2 times infinity plus 1 over 5 times infinity squared minus 3 times infinity minus 2. Let's try to evaluate this. So infinity squared is infinity. 2 times infinity is infinity. And you add number 1 to infinity, you still get infinity. In the denominator, we have 5 infinity squared, that's infinity, minus 3 times infinity, that's minus infinity, and you subtract 2, then it's still negative infinity. So we run into a small little problem here. First of all, the numerator, which is easy to estimate, is going to be infinity. But first of all, the denominator is undefined because we cannot subtract infinity from infinity because we don't know the exact size of infinity. So infinity itself is undefined. So we are trying to divide infinity by an undefined number. But even if we were to figure out some number in here, either plus or negative infinity, we can't even divide. So therefore, we're going to say this is impossible to determine because it's undefined. So next, we're going to think, how can we solve this problem then? So how can we determine what values of y approach as x approaches infinity? So the way we think is this. The source of our problem is having too much infinity in both numerator and denominator, which makes this expression undefined. And when I say too much infinity, which is kind of a random term or statement to make, the idea is that dividing infinity by an undefined number, so the presence of infinity in both numerator and in denominator, brought us to some expressions that are undefined. So now we're thinking, what brought in infinity? Because it seems that that was a problem. So infinity came in because x became infinity. So we are thinking, well, is it possible to simplify x in some ways so that we can determine the value of y? So the only way we can simplify x is if we factor out x to whatever power we can take out. The higher the power, the better. So in this case, just like we did in the example when we graphed ax plus b over cx plus d, we will take out x of the highest power from the numerator. So we have x squared, and the term x squared now becomes 1. The term 2x becomes 2 over x, and the term 1 becomes 1 over x squared. So if you need more explanations on how to get to this, please refer to the previous lesson where we explained it in more detail. So down in the denominator, we have again x squared as a common factor. That's the highest power. And then we have 5 minus 3 over x, and then minus 2 over x squared. So as you can see, if you expand it here, we still get the same function that we had before. But now we're allowed to eliminate x squared. And our equation, the equation of this function, is y equals 1 plus 2 over x, and I will substitute x by infinity at this point, 1 over infinity squared again, and then 5 minus 3 over infinity minus 2 over infinity squared. So now I hope we can see why we took out x squared, because at this point when we substitute x by infinity, these numbers where infinity is present are estimatable. So 2 over infinity is practically 0 plus. 1 over infinity squared is 1 over infinity, so 0 plus. 3 over infinity, that's a 0. And 2 over infinity squared is also a 0. So therefore, we're going to say that the value of y here would be equal to 1 plus a bunch of zeros, so number 1, divided by 5 minus a bunch of zeros, which is about 5. So therefore, we're going to say that the y value will be about 1 over 5. Considering that these are not exactly equal to 0, the y value won't be exactly 1 over 5. And that is the reason why we say that at y equals 1 over 5, the function will have a horizontal asymptote. Because at 1 over 5, or 1 over 5 is a value the function will never have, but it will get very close to. So in the same way, we can determine the horizontal asymptote by allowing x to approach negative infinity. And the process is similar, and I encourage you to try this process on your own, which means that substitute negative infinity for x, right? And then evaluate the value, the y, and see where the y values are going. In general, in the functions that we graph in the advanced functions course, the functions will have only one horizontal asymptote, which means that whichever horizontal asymptote we find in one side, we find on the other side as well. So now that we have looked into more horizontal asymptotes in a wider variety of rational functions, let's talk about how we determine horizontal asymptotes in different types of functions. Now, we can classify finding horizontal asymptotes into two strategies, or into two groups. Now, horizontal asymptotes, remember that are horizontal lines, and all horizontal lines will have the equation y equals a number, a constant number. Now, the first time we looked into rational functions, we saw that the horizontal asymptote was at y equals 0. And that happened when in the numerator we have a constant number. For example, we had the functions, or we looked at functions of the form y equals a constant number, let's say, for example, number 1 over mx plus b. Or we had y equals 1 over ax squared plus bx plus c. So we mentioned and emphasized that it doesn't really matter if this is a 1 or a constant, about any constant, 1 or any other number. It can be positive or negative. It doesn't really matter. Whenever we see a constant in the numerator, we'll say that the horizontal asymptote is always at y equals 0. Now, generally speaking, we're going to say that horizontal asymptote will be at y equals 0 whenever the degree of the numerator is less than the degree of the denominator. And as an example in here, I would bring up the function y equals x plus 1 over x squared. I just made this up, plus 3x minus 2. So notice that, or the rule that we created was that if we were trying to find the horizontal asymptotes in y equals ax plus b over cx plus d, then the horizontal asymptote was at y equals a over c. And when we look at functions that are in the form quadratic over quadratic, like the one here, we notice that the horizontal asymptote, again, was 1 over 5. So that makes us think that when the degree of the numerator and denominator is the same, we can find the horizontal asymptote as the ratio of the leading coefficient. Now, when we look at functions in the form linear over quadratic, again, we are trying to stretch the same idea. We can interpret them as functions with the term x squared with the coefficient 0, and then plus x plus 1 divided by 1 x squared plus 3x minus 2. And the horizontal asymptote here would be at y equals 0. So you can either remember the rule of writing the ratio of the leading coefficients, or you can remember that when the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will be at y equals 0. Now, horizontal asymptote will be at a number y equals some number different than 0. So it will be in the form y equals a number different than 0 if the degree of the numerator and denominator equal each other. So, like in the examples we saw before, linear over linear, we saw that horizontal asymptote was that ratio of leading coefficient. Quadratic over quadratic, ratio of the leading coefficients. So let's take a look at a couple of examples and practice how to find vertical and horizontal asymptotes. So horizontal asymptotes have become my favorites by default, actually, because I can easily determine their equations by just taking a look at or identifying the leading coefficients. So the leading coefficients for numerator are 5 and denominator negative 2. So therefore, we're going to say that horizontal asymptote is at 5 over negative 2. So, which you can write as negative 5 over 2. We get the idea. So for the vertical asymptote, we're going to set the denominator equal to 0. So 3 minus 2x squared equals 0, which will make 2x squared equal to 3, and x equal to plus or minus the square root of 3 over 2. So therefore, we're going to say that there are two vertical asymptotes in this case. One is root 3 over 2, and the other is at negative root of 3 over 2. Next, we're going to look at example B. So we'll start off with the horizontal asymptote. Again, numerator degree 2, denominator degree 2. So we can easily take the leading coefficients to calculate our horizontal asymptote, which is at 2 over 1, or simply we can say at y equals 2. For vertical asymptotes, we'll make denominator equal to 0 to find the restricted value, so that means x squared must equal negative 1, and this is not possible. So if this is not possible, it means that the function doesn't have restrictions. It means that there will be no vertical asymptotes. And that can happen, and we've seen graphs of functions with no vertical asymptotes. So looking at the next example, as you can see in here, we have x plus 3 over 2x squared minus 5. So this is linear, so first degree and second degree. So two ways we can actually determine the horizontal asymptote easily. So we can add the term x squared so that we have the same degree in both numerator and denominator, and then determine the ratio of the leading coefficients, or the horizontal asymptote as a ratio of leading coefficients. So y equals 0 over 2, or y equals 0, same thing. Or we can also remember the fact that degree of the numerator is less than degree of denominator, that automatically makes the horizontal asymptote at y equals 0. So the next thing we want to find is vertical asymptote. So 2x squared minus 5 equals 0. That makes x squared equal to 5 over 2, and x equals plus or minus root of 5 over 2. So we have two vertical asymptotes. One is at x equals root 5 over 2, and the second asymptote is at negative root of 5 over 2. Next example. So notice here we have a constant. Right away, we're going to think, oh, horizontal asymptote then must be at y equals 0. Whenever we have a constant in the numerator, horizontal asymptote is at 0. Now, if you want to look at it again the other way around, so you want an x squared term in the numerator so that you can match the leading coefficients, no problem. So that's 0x squared minus 4 over 1x squared plus 1, and 0 over 1 would be equal to 0. Vertical asymptote, again, same strategy. We're going to have to make x squared plus 1 equals 0, and we all know this is not possible, which means that this function doesn't have a vertical asymptote. So, no vertical asymptotes. Next, we're looking at 3x squared over 4x squared plus 1. Again, horizontal asymptote at 3 over 4. How do I know? Same degree, both numerator and denominator, and ratio of the leading coefficient, 3 over 4, and that's a horizontal asymptote. Vertical asymptote, we have to find the restrictions, and we're encountering too many equations or too many functions with no vertical asymptotes. So as you can see, this is impossible, and therefore we're going to say there are no vertical asymptotes in this case. And lastly, we have this little example here. As you can see, we have degree 2. That means the ratio of the leading coefficient is 7 over negative 2. That will make the horizontal asymptote at y equals 7 over negative 2. And the vertical asymptote is found by making the denominator negative 2x squared equal to 0, which means x squared equals 0 at x equals 0. So there will be one vertical asymptote at x equals 0. So this is how we find the asymptotes, and we're going to summarize now how we determine or how we go over the entire graph analysis of a rational function. So generally speaking, I'm going to say that to draw the graph of a rational function, we follow these steps. Number one, we want to factor the denominator because that will give us the zeros, or will help us find the zeros of the denominator. That help us in return to find the domain and determine the vertical asymptotes, which are at the restricted values of the domain. Horizontal asymptote will help us find the range. You find the x-intercepts by setting y equal to 0. Remember, in rational function, if you want to set y equal to 0, it means that you are setting the numerator, this expression here, equal to 0. So it's easy to remember it this way. Numerator equals 0, and so for x, and there go the x-intercepts. For y-intercept, we set x equal to 0 and evaluate y. And for n behaviors, what we try to do is, first of all, we look at the two ends, the far end, the left and the right end of the graph, by sending x to positive and negative infinity and finding where the values of y are heading, so what they're becoming. And also, we want to check the behavior of the function around the vertical asymptote. So we consider each vertical asymptote left and right, and we see what the trend in the y values would be. So we're going to start off with this example. It's a very simple, straightforward example. And I will start off with domain and range. So for the domain, I have to check and see where the x values, for what x values we have the denominator equal to 0. So as you can see here, we have two restrictions at x equals plus or minus 1. So therefore, we're going to say the domain will be any real number, but not x plus or minus 1. So domain is done. So based on this, we will determine the vertical asymptotes. So there will be two of them, one at x equals 1 and one at x equals negative 1. Next, I will try to determine the horizontal asymptote. For horizontal asymptotes, again, we're looking at the ratio of the leading coefficients, and the ratio of leading coefficient here in this case is equal to 1. And we're going to say that for the range, y values can be anything, but it's unlikely that they will be equal to 1. Now, we have to be very careful with this because as we explore more rational functions with variety of types of equations in numerator and denominator, having a horizontal asymptote doesn't necessarily mean it's a restriction in the range of the function, because vertical asymptotes, while vertical asymptotes are never crossed, horizontal asymptotes may be crossed in rational functions. Not in this particular one though, but we have to wait until we sketch the graph in order to determine whether or not the horizontal asymptote will actually set a restriction for the range. Next, we're looking into the intercepts. For x-intercept, we make y equal to 0, and we said we make the numerator equal to 0. And numerator equals 0 means x squared plus 1 has to be 0. So here's the numerator. And as you can see, x squared equals negative 1 is impossible. Therefore, no x-intercepts. For the y-intercept, we are going to set x equal to 0 and evaluate y. And the way I look at it is this. Wherever I see x, I make them disappear, and I only focus on the numbers, the constants. So 1 over negative 1, which means that the y-intercept is at negative 1. Now, next we're going to put everything here on the grid. We have two vertical asymptotes, and the vertical asymptotes are at plus and negative 1, plus and minus 1, positive and negative 1. That sounds better. And as you draw the asymptotes, also label them. It is very important, not just so that you show proper work, but also it's good for you to have an idea and a feel of what the numbers are around here. Okay, so next we have the horizontal asymptote, which is at y equals positive 1. And we'll label it. We'll say this is a horizontal asymptote at y equals 1. And we have a y-intercept, which is right at y equals negative 1. So we'll plot this. Now, before we graph, I want to mention something very important, which is symmetry. Symmetry is very helpful in analyzing before drawing the graph because it can save us a lot of time. If we notice that a function has even symmetry, for example, we only have to draw half of the graph and the other half is just a copy of one of it, all right? So the half that we have figured out. Or odd symmetry, same idea. So if you know part of the graph, then you will know where to draw the other one. So first I will check for even symmetry, which means I am trying to find k of negative x in this case. And k of negative x will be negative x to the power of 2, and then plus 1, divided by negative x to the power of 2 minus 1. So that would equal x squared plus 1 over x squared minus 1. And as you can see, that's exactly the same as k of x. So therefore, we're going to say that this function has even symmetry. Oops, here we go. Now, we're going to start drawing the graph. And the way we're going to do it this time is by using what we call testing point or the spying points. So we choose numbers or values of x from this part of the domain. Remember that the vertical asymptotes will divide the domain of your function into 3 parts. One here, one in between the vertical asymptotes, and then outside it. So what we do is we choose a value of x on the left side in here. Let's say, for example, x equals negative 2. So if x equals negative 2, you have negative 2 squared here. So that will make 4 plus 1, that's a 5, over 4 minus 1, which is a 3. So 5 over 3 will be somewhere here. So more than 1. Sorry, I'm going to pause it. And next, we're going to take a look at the graph of the function on this side. So I'm going to take a value of x close to the vertical asymptote on the right side of it now. And as an example, I'll take 0.5 negative. And I'll use a calculator to find out what the value of y becomes. So if we have negative 0.5 to the power of 2 and plus 1, and you're dividing it by 0.5 power 2 minus 1, then the answer would be a negative 1.66. So, which means that the graph will be heading down this way. So what we have in here is, first of all, the graph going down this way. We're going to work with 1/2. And if the function has a point right here, we're going to say that it has a horizontal asymptote. And the only way it can go is follow the vertical asymptote and follow the horizontal asymptote. And the shape of the graph will look like this. Now, if you want to be sure that you have found the graph or you've drawn the graph exactly where it's supposed to be, use another testing point a little bit further to the either left or right of your point that you have chosen, or the chosen point from before. And now that I have half of the graph and knowing that the function has symmetry, I would continue drawing the rest of it. So even symmetry means that on the other side of the y-axis, I will see the same thing, and I will have, again, this same curve on the other side. And voila, this is the graph of the rational function x squared plus 1 over x squared minus 1. I hope this made sense. Thank you for learning with me, and bye for now.